Sklearnutilsmetaestimators. Description: meta-estimators in scikit-learn. Sklearn are a powerful concept that allows you to build complex machine learning pipelines by combining different estimators into a single unified structure. They provide a convenient way to encapsulate and reuse common machine learning patterns, simplifying the development and deployment of sophisticated models. Inputs: estimators, one or more base estimators, which are the core building blocks of the meta-estimator. These estimators can be classifiers, regressors, transformers, or other compatible sklearn models. Parameters: configuration settings for the meta-estimator, including hyperparameters for the underlying estimators and control parameters for the meta-estimator's behavior. Outputs: predictions output of the meta-estimator, typically in the form of class labels, regression values, or transformed data, depending on the specific meta-estimator and the task at hand. Fitted model: a trained meta-estimator, containing the learned parameters of the underlying estimators and the meta-estimator itself. Steps: initialization: the meta-estimator is created with specified base estimators and hyperparameters. Training: the meta-estimator is fit to the training data, which typically involves training the underlying estimators and potentially learning additional parameters. Prediction: the trained meta-estimator is used to make predictions on new data, utilizing the trained underlying estimators and its own logic. Metrics: performance metrics, evaluation metrics relevant to the task, classification accuracy, regression error, etc., are calculated to assess the effectiveness of the meta-estimator. Model complexity metrics like the number of parameters or model size can be used to understand the complexity of the meta-estimator. Visualization plots: decision boundary plots visualize the decision boundaries learned by classification models. Feature importance plots show the relative importance of features in the model. Residual plots for regression models visualize the difference between predicted and actual values to identify patterns or outliers. Fine-tune parameters: hyperparameter optimization search for optimal values for hyperparameters using techniques like grid search or random search. Feature engineering experiment with different feature transformations to improve model performance. Uncertainty methods: confidence intervals calculate confidence intervals for predictions to estimate the uncertainty associated with them. Bayesian inference: use Bayesian methods to model the uncertainty in model parameters. Challenges and fixes: challenge 1: overfitting. Meta-estimators can overfit if the underlying estimators are too complex, or if the hyperparameters are not carefully tuned. Sample use case that resulted in challenge 1: using a high-capacity neural network as an underlying estimator without proper regularization. Fixes to challenge 1: regularization. Apply regularization techniques L1, L2. Dropout to the underlying estimators to prevent overfitting. Early stopping: stop training when the model's performance on a validation set starts to decline. Challenge 2: poor generalization. Meta-estimators can have poor generalization performance if the training data is not representative of the real-world data. Sample use case that resulted in challenge 2: training a model on a small dataset with limited diversity. Fixes to challenge 2: data augmentation. Generate synthetic data to increase the size and diversity of the training set. Data preprocessing. Apply appropriate data preprocessing techniques to ensure that the data is consistent and suitable for training. Challenge 3: computational complexity. Some meta-estimators can be computationally expensive to train and predict. Sample use case that resulted in challenge 3: using a meta-estimator with a large number of Underlying estimators or complex operations. Fixes to challenge 3. Efficient algorithms utilize optimized algorithms or libraries for training and prediction. Distributed computing distribute the computation across multiple machines for parallel processing. Challenge 4. Interpretability. Meta-estimators can be difficult to interpret, especially if they involve multiple layers of estimators. Sample use case that resulted in challenge 4 using a deep learning meta-estimator with a complex architecture. Fixes to challenge 4. Feature importance analysis. Analyze the importance of features to understand the model's decision-making process. Visualization techniques utilize visualization tools to visualize the model's behavior and decision boundaries.